This training module is an overview of methods for modeling runoff modification by stormwater best management practices, BMPs. This is training module 9.01a for the Stochastic Empirical Loading and Dilution Model SELDM. This training module has 19 slides and will take about 13 minutes. It was prepared by the U.S. Geological Survey in cooperation with the Federal Highway Administration. This training module has 5 learning objectives. At the end of this module, you should be able to name the 3 general BMP processes, discuss the importance of each process, describe uncertainties in modeling BMPs, identify the probability distribution used to model BMPs, and describe the reasoning for using rank correlation. This presentation is a brief overview of the technical details for simulating stormwater best management practices. Please see the BMP report, USGS Scientific Investigations Report 2014-5037, and the SELDM Manual, USGS TM4C3 for more details. We will be publishing a new BMP report in 2020 with updated and expanded data and statistics calculated by using data in the December 2019 version of the International BMP database. Structural stormwater best management practices affect downstream flows and loads by reducing runoff flows and loads and by extending the runoff hydrograph. The downstream flows and loads are the sum of the upstream and highway or urban runoff flows and loads. Downstream concentrations are the downstream loads divided by the downstream flows. BMPs can improve downstream water quality when they reduce runoff contributions. BMPs also can reduce downstream concentrations by extending the runoff discharge hydrograph over a long period of time. Therefore, flow reduction, concentration reduction, and hydrograph extension are the 3 primary BMP treatment mechanisms. Reducing concentrations reduces effluent and downstream loads. This cartoon from the US EPA indicates the potential effect of concentrations on discharge loads and therefore the potential effect on concentrations in receiving waters. This cartoon shows that if you cut the concentration in half without changing the runoff volume, then you cut the load in half. Flow and concentration reductions have a multiplicative effect to reduce effluent loads. This cartoon from the US EPA indicates the potential effect of concentration and flow reductions on discharge loads and therefore the potential effect on concentrations in receiving waters. If you cut the concentration in half and the runoff volume in half, then you cut the load by 3/4. What is discharged to the stream is half of a half, which equals 1/4. Hydrograph extension by BMPs increases dilution of runoff in downstream flow. The diagram on the left shows the runoff hydrograph from a basin upstream of site of interest and 2 potential hydrographs from that site. The hypothetical graph on the right shows the cumulative percentage of the total upstream storm flow that occurs as the storm progresses. The diagram shows 2 potential runoff hydrographs from the site of interest, one with a short duration, D1, and the other with a longer duration, D2. This longer duration hydrograph may represent the effect of design changes or use of best management practices that slow runoff flows. For example, using a grassy swales to route runoff instead of a sewer pipe may slow the discharge of runoff, and use of a retention pond also may extend the outflow. In this example, only 15% of the upstream storm flow occurs during duration 1 and about 55% occurs during duration 2. Thus, use of the drainage designs and best management practices that extend the flows from the site of interest results in increased dilution of runoff flows. BMP processing is complex and varies from storm to storm, site to site, and BMP to BMP. This diagram shows a source area on the left, a BMP in the center, an overflow or bypass route above the BMP, and the receiving water on the right. The flow terms are shown in blue and the concentration terms are shown in yellow. The loads are the product of the flows and concentrations. Flows may be attenuated by infiltration, evaporation, and transpiration. Concentration reduction mechanisms include settling, filtration, adsorption, volatilization, flotation, and various biological mechanisms including uptake, conversion, and degradation. It is generally assumed that overflow and bypass flows are by and large untreated. Overflow BMPs in which flood flows are routed through the BMP seem to be more common because the ratio of overflow to bypass BMPs in the International BMP database is about 2.85. It's important to note that these processes vary with air temperature, water temperature, solar energy, which will vary within storms, from day to night, from storm to storm, and from season to season. As an example of potential variations in BMP performance, this graph shows variations in sediment settling velocities with variations in size, specific gravity, and water temperature. The fall velocity in feet per year is shown on the vertical axis, and the sphere diameter is shown on the horizontal axis. Fall velocity varies by 9 orders of magnitude as grain size varies over 5 orders of magnitude. Increasing the specific gravity from 1.5 to 2.5 about doubles the fall velocity for a given grain size and water temperature. Increasing the temperature from 0 to 30 degrees C about doubles the fall velocity for a given grain size and specific gravity. Studies indicate that the specific gravity of highway runoff solids range from about 1.6 to 1.75. This graph shows the variation in particle size distribution among 94 storms. The percent finer than a given grain size is shown on the vertical axis, and the grain size is shown on the horizontal axis. This data shows the range in particle sizes is large, and the storm-to-storm variation is huge. The red line is the commonly used distribution from the National Urban Runoff Program values by Driscoll in 1986. If we were trying to simulate even the simplest BMP and most common treatment method, gravity settling, we could be way off with a deterministic model. And obviously, a study with few events may not really characterize treatment if grain size distributions vary this much in urban and highway runoff.
Modeling the effectiveness of BMPs is difficult because there are many different types of BMPs, and they can be used in series or, less commonly, in parallel. As these images indicate, the characteristics of the flow path through the BMP can be quite different from BMP to BMP. The treatment mechanisms vary by design, between designs for the same type of BMP, and from storm to storm and season to season at each BMP site. The performance of BMPs also change as the BMP ages and between cleanouts if a BMP is actually maintained. SELDM uses a black box approach to model the net effect of one or more BMPs at a site of interest because there are so many complexities. Data for characterizing detailed processes over long periods of time are generally lacking, and there is great uncertainty in the application of data from site to site and storm to storm. With the black box approach, we are given the flows, concentrations, and loads from the source area and use transfer functions to calculate the flows, concentrations, and loads to the receiving waters. In a black box model, we can focus on the net effect of the BMP or BMPs on receiving water quality. In SELDM, these transfer functions are stochastic ratios of outflows to inflows with rank correlation to inflow values. There are two methods for modeling the effect of source control. We must ask, do we model the effects of non-structural BMPs by reducing source concentrations or by improving BMP treatment ratios? SELDM does not have an explicit source control option, but the SELDM modeler may use either method to simulate the types of improvement. This may be a case where professional judgment is used in consultation with regulators and stakeholders to inform a planning level analysis of the effectiveness of such measures. In this case, SELDM can be used to test the effect of different assumptions on the number of water quality excursions downstream of the outfall. In SELDM, volume reduction, concentration reduction, and hydrograph extension variables are modeled by using the trapezoidal distribution and the rank correlation with the associated storm runoff variables. This family of distributions was selected for modeling BMP performance measures because it can be parameterized by using expert judgment or by fitting the distribution to data if good data are available. The triangular distribution, which is a special case of the trapezoidal distribution, commonly is suggested when uncertainties in input data are large. The trapezoidal distribution is bounded by a selected minimum and maximum value. When data are uncertain or are limited in scope, use of a bounded distribution reduces the chance that unrealistic output values will be generated by extrapolating a distribution beyond the range of available data. The trapezoidal distribution is parameterized by selecting a lower bound, the minimum value, a lower bound of the most probable value, an upper bound of the most probable value, and the maximum value. The trapezoidal distribution is very flexible and can assume a variety of shapes, including a positive skewed triangular distribution, a negative skewed triangular distribution, a symmetric isosceles triangular distribution, and a rectangular uniform distribution. These diagrams show the extreme negative or left skewed triangular distribution and positive or right skewed triangular distribution. In the first diagram on the left, the lower bound of the most probable value, the upper bound of the most probable value, and the maximum value are equal. In the second diagram on the right, the minimum, lower bound of the most probable value, and upper bound of the most probable value are equal. Although the three statistics are equal for each of these triangles, we can see that the vast majority of values will fall between the vertical line and the opposite side of the triangle. For concentration and flow reduction, the first two steps are to get paired data and calculate ratios. The graph on the left is a scatter plot showing inflow and outflow concentrations of total phosphorus from the Lake Ridge detention pond in milligrams per liter. The vertical axis is a log scale showing the outflow concentration in milligrams per liter. The horizontal axis is a log scale showing the inflow concentration in milligrams per liter. The graph on the right is the scatter plot showing the inflow concentrations on the horizontal axis and the unitless ratio of outflow to inflow concentrations on the vertical axis. The next step is to calculate the ranks of inflow concentrations and calculate the rank correlation between inflow and the ratios. The graph on the left is a repeat of the scatter plot showing inflow concentrations on the horizontal axis and the unitless ratio of outflow to inflow concentrations on the vertical axis. The graph on the right is a scatter plot with linear axes showing the ranks of the ratios and inflow concentrations. The scatter plots of the data and the ranks of these data show that the ratios decrease with increasing flow concentrations. Spearman's rho for this dataset is about minus 0.76, which means that the ratios decrease with increasing concentration. The next step is to fit the trapezoidal distribution to the ratios. Least squares optimization was used to fit the BMP monitoring data to the parameters of the trapezoidal distribution. This graph shows the result of the fitting process for the total phosphorus concentrations. The concentration ratios are shown on the linear vertical axis, and the percentage of values less than or equal to a given value are shown on the horizontal axis. The data are shown as white circles, and the best fit cumulative distribution function is shown as a yellow line. The trapezoidal statistics in the upper left are the best fit values for this data set. In this training module, we learned that concentration reduction, flow reduction, and hydrograph extension are the processes that mitigate runoff effects. Concentration reductions and flow reductions reduce the load to receiving waters. Hydrograph extension increases dilution. There are many unit processes that vary in time with location and in different types of BMPs. Because the situation is complex, a stochastic black box model may provide the needed information. SELDM simulates BMP treatment by using stochastic ratios in a trapezoidal distribution with correlations to inflow values.